Welcome to the tutorial on how to design PI controllers for DC motor drive using Control Design tool in Simulink. The controllers that we are going to design in this tutorial are for the DC motor drive that is based on Cascade control structure as shown here. In DC motor drive shown here, there are three loops: the top loop, the speed loop, and the position loop. The Cascade control structure is characterized by its multiple loops, with a reference to the inner loop is coming from the output of the controller of the outer loop. The top reference for the top loop is coming from the speed controller of the speed loop, and the speed reference is obtained from the position controller. Therefore, we can easily claim the references for each loop to its maximum allowable values. For example, if we want to limit the armature current to a certain value, then we can do that by clamping the top reference. Similarly, the speed can be clamped to its maximum allowable speed. The innermost loop, that is the top loop, must be designed with the largest closed-loop bandwidth, or in other words, fastest response. And the outermost loop, which is the position loop for this DC motor drive, should have the smallest closed-loop bandwidth, or slowest response. We can design the controllers for each loop independently, provided that the closed-loop bandwidth for each loop is separated by at least a decade from each other. In our tutorial, we will be controlling the speed, therefore the position loop can be disconnected. I will show you how to design the PI controllers for the torque and the speed loops. To design the controllers systematically, we need to have the linear models of all the elements in the control system. If the system is non-linear, for example the power electronic converter, then we need to average and linearize it first. In this tutorial, I will not go into details on how to linearize the power converter, but rather I will just present the results. If you are interested in knowing how to linearize the power converter, or how to obtain the linear model of the power converter, you can find them in most power electronics textbooks or in my other lectures. The contents of the tutorial can be divided into two parts. In the first part, I will briefly present the control and modeling of power converter and the DC motor. In the second part of the tutorial, we will switch to MATLAB Simulink, and I will show you, using the control design tool in Simulink, how the controllers for the torque and speed loops can be designed. First, let's consider a two-quadrant DC-DC converter. The quadrant of operation for a motor is characterized by its speed versus torque graph as shown here. For a converter, the quadrant of operation is characterized by its average voltage and average current, which means that for a two-quadrant converter, the average voltage Vt cannot become negative. However, the average current can reverse its directions and becomes negative. The converter consists of two power transistors or power switches and two diodes. The input voltage is VDC and its output voltage is Vt, which is connected to the armature of the DC motor. Ra is the armature resistance of the DC motor. The instantaneous value of the output voltage Vt depends on the switching states of the power switches. If the upper switch T1 turns on and the lower switch T2 turns off, then Vt equals VDC. And for positive current or positive IT, the current will flow through T1. Whereas for negative IT, in which the current reverses, then the current will flow through D1. If T2 turns on and T1 turns off, Vt equals 0. For positive current IT, the current will freewheel through D2. And for negative current IT, it will freewheel through T2. The positive or negative current is determined by the magnitude of the motor back EMF EA and the average voltage Vt. If the average voltage Vt is larger than EA, positive current will flow. On the other hand, if the average voltage of Vt is smaller than EA, negative current will flow. To control the average voltage Vt, we need to control the duty cycle of the instantaneous Vt. One way of controlling the duty cycle is by comparing a control signal with a triangular wave. If control signal Vc is larger than V triangular wave, then the output of the comparator becomes high and the upper switch is turned on. On the other hand, if Vc is less than V triangular wave, the output of the comparator goes low and the lower switch is turned on. In this way, the duty cycle of Q, which is the output of the comparator, will directly proportional to the average output voltage of the converter. In our tutorial, we will be using a 4-quadrant converter, or also known as H-bridge converter. If you look closely, a 4-quadrant converter is essentially a combination of two 2-quadrant DC-DC converters. In this 4-quadrant converter, in addition to VDC and 0, the instantaneous output voltage can be made to equal minus VDC. Assuming a positive current flow, this can be obtained by turning on T4 and T3, and the current will flow through T4 and D3. If the current is negative, then it will flow through T3 and T4. Therefore, to implement a given positive average voltage, for example, we can make the instantaneous voltage to swing between VDC and minus VDC instead of VDC and 0 as we have seen in the 2-quadrant converter previously. This also means that by alternating between VDC and minus VDC, we can make the average voltage negative by changing the duty cycle. This switching scheme is known as bipolar switching scheme. Alternatively, the same average voltage can be achieved by swinging the voltage between VDC and 0 or minus VDC and 0. To get a 0 voltage at the output, the current will freewheel through a diode and a transistor. For a positive current, it will flow through T1 and D3 or D4 and T2. On the other hand, for a negative current, it will flow through D1 and T3 or D2 and T4. This switching scheme is known as unipolar switching scheme. As I said earlier, that I will not go into details on the modeling of the converter. I'm not going to show how to obtain the relationship between the average voltage Vt and the control signal Vc. If you are interested in this, you can find them in most power electronics textbooks or in my other lectures. The relationship between average Vt and Vc for 2-quadrant and 4-quadrant converters are just DC gains as shown here. VDC is the input DC voltage to the converter, and VTRI or VTRI P is the peak of the triangular waveform. We immediately notice that the gain of a 4-quadrant converter is twice as high as the 2-quadrant converter, regardless of whether it is a bipolar or unipolar switching schemes. The gain for a 4-quadrant DC-DC converter is the same. In this tutorial, the 4-quadrant DC-DC converter will be used in the controller design. Now let's move on how to model a DC motor. What is shown here are the circuits for the armature and field of a DC motor and their respective voltage equations. In this tutorial, the permanent magnet DC motor is assumed. Therefore, the field circuit is irrelevant to us. The permanent magnet DC motor can be completely modeled using 4 equations: the armature voltage equation, the electrical torque equation, the mechanical torque speed equation, and the back EMF equation. To obtain the small signal model, as usual, we have to linearize these equations by introducing small perturbations around the DC operating points. The DC and AC equations are then separated. The small signal model is derived by performing the Laplace transformation to the AC equations. And from these equations, a DC motor block diagram can be constructed. The small signal block diagram of the DC motor shown here will be constructed in Simulink and used in designing the controller. If you are interested in to see how the parameters of DC motor influenced the location of the poles in the characteristic equation, you can perform block diagram reduction as shown here. as we can see that the characteristic equations of the transfer function between the current or torque and armature voltage, or between the speed and armature voltage, contains two poles. These poles can be real poles or complex poles, depending on the numerical values of the motor parameters. For this tutorial, since we are using small motor, the poles are real. Now that we have linear models of the power converter and DC motor, we are ready to design the controllers. The parameters for the permanent magnet DC motor that we will use are shown here. The switching frequency FSW, which is the frequency of the triangular wave, is set to 20 kHz. Therefore, we will design the closed-loop bandwidth of the top to be a decade lower than this, which is 2 kHz or 12.56 kiloradian per second. This is a non-linear block diagram of our top loop, and this is its equivalent small signal model. This is a converter model, the PI controller, and the DC motor block diagram. Once we have designed the top controller, we can proceed towards the outer loop controller design, that is the speed controller. We have the options of replacing the top loop that we have designed with a unity gain block. As far as the frequency at the vicinity of the speed bandwidth is concerned, which is a decade lower than the top bandwidth, the gain of the top loop is 1. In this way, the dynamic of the speed is just governed by B, which is the viscous friction constant, and J, which is the moment of inertia of the rotating system. Before we proceed with the control design tool in Simulink, let us define the control specifications for our DC motor speed control system. During the transient states, such as during acceleration, the linear model that we have developed is not valid. So designing the controllers to fulfill the transient requirements, such as percentage overshoot, rise time, or settling time, is not a good choice. Let me give you an example. Consider the block diagram of a closed-loop speed control for a permanent magnet DC motor as shown here. There are two control loops, torque loop and speed loop. As I have mentioned before, the reference torque is coming from the speed controller. In practice, we normally limit the torque reference to either limit the armature current or to limit the acceleration. During transients, for example, whenever there is a step change in speed reference, the speed controller will produce a large signal to compensate for large speed error. This large signal most likely will hit the maximum torque reference or torque limit that causes a saturation to the torque reference. Therefore, the relationship between the speed error and the torque reference is no longer linear. So too is the output of the converter. When maximum duty cycle, that is 1, is reached, for example during large acceleration, the converter is no longer a linear DC gain. In other words, the relationship between VA and VC is no longer linear during the acceleration or transient. So our model is not good during transients, unless, of course, the torque limit and the DC input voltage of the converter are sufficiently large. So what should be our control requirements? In most of the cases, we want the response to be as fast as possible, with minimum oscillation and good stability. To fulfill these requirements, it is sufficient for us to use body plot. Large bandwidth that is limited by the switching frequency, of course, translate to fast response. Good phase margin, typically larger than 65 degrees, translate to good stability with less oscillation. So, in our example for this tutorial, our control specification would be just large control bandwidth with phase margin of 65 degrees, and also to ensure zero steady-state speed error, the DC gain for the open loop transfer function has to be infinite or very large. And all of this can be achieved by using body plot, as we shall see later. Okay, we will now switch to Simulink for the second part of the tutorial.